computation in GPUs. So if you know about convolution, stencil computation is pretty similar to convolution, but not exactly similar. We'll discuss the differences and similarities. So a little background. Uh, let's see what a structured grid is. Structured grid is any, like, this is a structured 1D grid, this is a structured 2D grid, and similarly in 3 dimensions. Any grid in n dimensions is a structured n-dimensional grid. And uh, stencil computation, this technique particularly, is used for solving partial differential equations. And I mean, is what I haven't ever used this, but from reading I understood that it's used in solving partial differential equations. And also, like, in um, if you have a, by partial differential equation I mean, like, if you want to find the uh, d by dx of something, or d square by dou x square, or dou square by dou y square, or dou by dou y of a function, all of these terms are part of a partial differential equation. And so definition of stencil is a geometric pattern of weights applied at each point of a structured grid, it seems. um, okay, so and another terminology here is order of stencil, where uh, like, if we have a 1D grid and we want to find the derivative at this point, that is um, derivative of function with respect to x at this point, we can just, if we know the value at this point and this point, let's say this is the function at I, function value at I, this is I, this is I minus 1, this is I plus 1. If we need to find this, we can say that f of I, this from Taylor expansion we know this, right? Where um, like f dash of I, or df by dx at I, is equal to f of I plus 1 minus f of I minus 1 by 2h, plus order of h square, an error, so we just neglect that. So we have this formula. So if we call this an order 1 stencil, because the highest order of derivative is 1. Similarly, if we also have terms of, like, dou square f by dou x square, we use our second order. And if we have dou cube by dou x cube, we use third order. Similarly, we extend this to 3 dimensions and 2 dimensions. Like, this is a 3-dimensional, these two are 3-dimensional grids, these two are 2-dimensional grids. And the examples we discuss here do not assume that variables are independent of each other. So if we have a function which is a function of x, y, and z, let's say, then x, y, and z are independent of each other. So x does not depend on y, y does not depend on z, and x does not depend on z. So dou f by dou x, dou y, dou square f by dou x, dou y, which is essentially dou by dou x of dou f by dou y, would be 0. Okay. Now we discuss what stencil sweep is. It's just one iteration of stencil. Now we look at the actual algorithm. So if we have a 2D 5-point stencil order 1, what does that mean? That means that to find the derivative, we are interested in these two terms. So to find these two terms, we need this point, this point, this point, this point, this point, the value of f at these 5 points. This is why we call it 2D 5-point stencil order 1. Okay. Now, um, so if this is the input and this the inner thing is the output, because we assume that for solving partial differential equations, the boundary pixels are typically ignored because they're not of any significance. So, for example, if we want to find the value here, we'll need the pixels here, here, this. So this is why all of the blue pixels highlighted are the pixels that will be used in the computation. But we won't be computing the stencil values, the output values for these pixels, because these are outside the boundary condition of the PDE. And similarly, this is a 3D 7-point stencil, which is a natural extension of 2D 5-point stencil of order 1. So this is just a basic stencil sweep kernel, which in which every we split the grid into blocks, and every each thread inside the block is responsible to for doing its own computation. So we see that only these threads do computation. Like if the thread is in the non-active region, we filter it out according to this condition. Okay, and we just calculate the value here is uh, like some function of these 5 points, and like this kernel is for 3D 7-point stencil, so this is just an extension of this 2D idea in 3 dimensions. So, and in 3 dimensions we have 7 such points, and let's say like the coefficient while we multiply is c1 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 c2 c3 c4 in 2 dimensions. In 3 dimensions will be the coefficients will be c0 to c6. Okay, but the problem with this approach is that the arithmetic intensity is pretty low, and the reason being, um, like for each thread, consider this thread for example. In the 3 dimensional case, how many floating point operations are there? So we have 7 points, right? So we have 7 multiplications plus 6 additions. These many floating point operations divided by the bandwidth, the memory transfers. So how many memory transfers from global memory does this require? Does this particular thread require? It requires like 1, 2, 3, 4, 5, right? So 5 into 4 bytes, which is like 13 by 20 flops per byte. Wait, 7 into 4? Oh yeah, sorry. The 5 is for 2 dimensional case. For 3 dimensional case will be 7. So 13 by 28 flops per byte, which is pretty low. We want this to be higher. So uh, I mean, the one of the ways we can improve this ratio is like we did in convolution. We can use shared memory, so that the number of global memory loads per thread comes down. Because if we use shared memory, the number of global memory loads per thread will be less, because uh, some threads, like initially in there'll be a two phase algorithm, where in the first phase threads collaboratively load global memory into shared memory only once, and then in the second phase thread use the data from shared memory. So the global memory transfers would only happen here, and there'll be less global memory redundant transfers. So if we use okay, and let's do a best case analysis where if um, okay, so the best case scenario would be if the entire input matrix can be loaded into the shared memory at once. So that would mean that each input pixel is loaded from the memory exactly once, and of course the flops per thread would remain the same, right? So in this case, the best ratio would be flops per thread by memory accesses in per thread into 4 byte, or at the grid scale it would be flops per grid into divide by memory accesses in grid into 4 bytes. um, I mean, we could do it in a per thread basis also, but the memory access per thread would be amortized per thread. So instead of that, let's do a per grid analysis. So flops per grid can be written as number of threads in grid into flops per thread. So flops per number of threads per grid is n square, and flops per thread is like for okay. So in case of convolution, the flops per thread was 9 into 2, because each we have a multiplication with the kernel filter corresponding elements. So we have 9 multiplications and then 9 additions, right? Okay, so this is the number of flops in convolution, and memory accesses per grid is n square into 4 bytes. So each data point in the grid is loaded exactly once. So the best case scenario in case of convolution is 4.5 ops per byte. But in convolution, the memory accesses in grid, um, that remains the same, because the best case scenario would be uh, every uh, data point is loaded at exactly once. But the flops per grid would actually decrease, because flops per grid again is flops per thread into number of threads in the grid. Number of threads in grid is n square, and flops per thread is 5 into 2, around 5 into 2. Or we could also do it in 5 plus 4, because 5 multiplications, so 5 like multiplications of the input pixel with corresponding coefficient, plus 4 number of additions. Actually depends on how we are implementing it. We could implement it as 5 plus 4 or 5 plus 5. So 5 plus 4 case would be if we manually add, like if we do C naught I naught plus C1 I1 plus C2 I2 plus C3 I3 plus C4 I4. So this would have like 1, 2, 3, 4, 5 multiplications and 1, 2, 3, 4 additions. Or 5 plus 5 would be the case where we like do sum is equal to 0 and do a for loop for 5 iterations and do multiplication, like sum plus equal to the corresponding multiplication. So in this case, the number of flops will be 5 multiplications and 5 additions. So that is 10 flops. So yeah, we have this best case ratio. We already see that the compared to convolution, the benefit of loading an input grid point value into shared memory for a stencil sweep would be lesser, and this difference would increase for like higher order stencils. So an implementation of this is we just every thread is responsible for loading its own um, uh, data point from the global memory into shared memory, and then using that value from the shared memory to do the computation. Now another optimization we can do is so an observation here. So an observation here is, since we are loading the tile into shared memory, we are, and for a 3D stencil, the shared memory used is proportional to t cube, right? Because the tile is t, has a size of t, and we are dealing in 3 dimensions, which is a severely limiting factor, because for even we cannot use bigger values of t because of the restriction on the shared memory size. So we would want to, so yeah, so it is written here, two major it's a disadvantage of small value of t. The first is it limits the reuse ratio. So they've calculated this. How did they calculate this? Okay, so this is a calculation of actual flops per byte. Okay, so let's calculate. If everything is loaded into shared memory in first phase, and in the second phase we use the shared memory, so the number of um, per in the grid, the number of uh, uh, bytes loaded from the global memory would be uh, sorry, not in the grid, per block. Let's do a per block basis analysis. So per, since shared memory is like done on a block level, so per block the block size is t cube, and each thread of the block, so t cube threads per block, and each thread loads 4 bytes, and the number of flops in the block is number of threads that do this computation. And we see that only the inner threads do the actual computation, right? Because the outer threads are just inactive. Yeah, so the number of inner threads in each dimension is t minus 2. So this is the number of active threads in the block, and each thread does 13 computations. So this is the calculation for OP per ops per byte, and we see that for smaller values of t, the for smaller values of t, okay, yeah. So for smaller values of t, the arithmetic intensity, that is the ops per byte, is low, which is bad. And the reason for smaller value of t is because of shared memory restriction. And what is the second? Oh yeah, and the second advantage is also disadvantage is also the adverse impact on memory coalescing, because for a smaller value of t, let's say we have a 8, t is equal to 8 and a two-dimensional um, grid. So 1 2 3 4 5 6 7 8. So when um, each warp consists of 32 threads, right? So it will consist of 4 rows being loaded. um, yeah, so 4, when we load 4 rows, that means per warp we are making 4 separate um, memory transfers. Instead, if we had a 32 cross 32 block, one warp could just have loaded the entire row at once. So we would have had just one global memory transfer per warp. Yeah, so that is a problem. So the need for larger T motivates the approach that we are going to cover, and the approach is thread coarsening. So the idea is, instead of allocating shared memory in 3 dimensions, why not allocate shared memory in 2 dimensions and use thread coarsening to iteratively, uh, instead of describing threads inside the block in 3 dimensions, we just, and each thread in that three dimensional space does some computation. Instead of that, why don't we describe the threads as a two-dimensional structure in a three-dimensional grid, and make sure that each thread in that two-dimensional plane does iterative work to cover the three-dimensional grid space, block space. So what I mean by this is, instead of, like, we originally had this three-dimensional uh, grid, right? And each thread in that grid was doing some computation. Now the grid would still remain three-dimensional, but block would remain two-dimensional. So this, like, let's say the grid is divided into blocks like this. Okay, into blocks like this, but this current block has only, for example, 4 cross 4. The block dimension is 4 cross 4, and these 4 cross 4 threads in iteration 1 operate on this xy plane, in iteration 2 operate on this xy plane, iteration 3 they operate on this xy plane, iteration 4 they operate on this xy plane. And after 4 iterations, the 4 cross 4 threads are able to do the entire computation that the 4 cross 4 cross 4 threads would have done if we had used a three-dimensional um, like thread structure per block. Okay, and yeah, so the code for this is like the iterative approach I just talked about. So every thread iterates for outer tile dimensional for um wait each thread iterates for for outer dimension outer tile dimension size times here. um okay, so and each thread, like if we are in this iteration, the second iteration, this thread would require access to this and this values also, like in the previous plane and then in the next plane. So instead of loading just one xy plane into shared memory, we load three xy planes into shared memory. Okay, cool. So the code is like, we first define the three xy planes in shared memory, uh, define the two xy planes in shared memory and the third one also. Once that is done, and this is the iterative loop. So okay, and in each loop, iterative loop, after each iterative loop, we update the previous, current, and next previous and current shared memory 2D structures, update them, and also initialize the next 2D structure. Yes, like just load from global memory into the next shared memory 2D structure. So in each iteration, once the three shared memories here, after saying threads, the three shared memory planes are ready for further computation. So once they're ready, we just do our simple like computation. This is just a simple computation. Okay, and what is okay? Yeah. This is done. So this was thread coercioning, and now another like observation here is that this thread needs access to this tile, this tile, this tile, this tile, the one below and the one above, right? Like in three dimensions. But we are oh, sorry, my bad. Wait. So this thread needs access to this thread, this thread, this thread. Four threads, four data points in the xy plane, and two data points in the z plane. Okay, but like since the data reuse in the z plane is not that much, if you think about it, like this thread needs just access to these two threads. This thread requires access to just these two data points from the other planes. So why are we um like, how do I put it, in two dimensions? It makes sense to load the entire thing into shared memory because this thread requires access to this data points, right? And this thread requires access to this. So each data point, if we don't use shared memory, will be loaded uh, by four threads four different times. There will be four times data use. But in this three-dimensional case, with thread coercioning, each data point uh, in the z direction, each data point is just loaded. Um, Two times? Two times, right? Wait, let me think. Uh, oh yeah, so there's no need to even like load these two other planes because w- while we are at, let's say, z is equal to 0, it needs access to z is equal to 1, right? So first we load z is equal to 1, like the corresponding, if this is x is equal to 0, y is equal to 0, we load x is equal to 0, y is equal to 0, z is equal to 1 into shared memory, and then use the shared memory data to do the computation for this thread, for this thread point. But when we so we essentially load the variable at x is equal to 0, the data point at x is equal to 0, y is equal to 0, z is equal to 1 once into shared memory, and use that for computation once. But what if we just loaded the data at x is equal to 0, y is equal to 0, z is equal to 1 into a register for this thread instead of using shared memory? Even then there'll be just there'll be just one global memory transfer, right? Because earlier there was a global memory transfer from global memory to shared memory, and then we are using the shared memory to do the computation. Now there's a global memory transfer from global memory to register, and we are using the register. And this way we are not even using three times the shared memory. So if we just have to allocate like one xy plane worth of shared memory instead of three xy planes of shared memory. So this is what is called register tiling. So you can see that instead of three shared memories, we use three floats. And first, for the current thread, we load the uh, previous value into a register, load the current value in the register. Uh, yeah, previous value in the register, current value in the register, and for each iteration load the next value into register, sync threads, and this is the same computation. Yeah, so this was all about stencil computation. Yeah, pretty neat actually.